Problem?
Are we giving you the...
In the next class. In the next class.
Next class is tomorrow?
Whenever the next class is. I don't have the energy to take assignments today, because then I have to carry them back to the office and file them away, and today is not the day for that. Maybe tomorrow will be, but not today. Physics. No. DIFC physics. Mechanics. Center of gravity. And begin. Right. I think this is okay with the light. Do you?
Yeah, it's fine.
It's okay? Yes. Well, it's okay for you, but...
I'm colorblind, so if it's okay for me, it should be good for others.
Possibly. Or maybe somebody else has I don't know, some other thing. Alright. People with glasses, this is okay? Yes, you can see it okay? Are you sure you can see it? Okay. Center of gravity. So, this is what we're looking at. So there's no homework to do. Yeah, does it make much of a difference? There's not much light coming in from the outside.
Yeah.
I would say that would make... It made exactly zero difference.
I tried.
But your effort is appreciated, thank you. Okay, center of gravity. Did you write that down? Yep. Right, so. What exactly, are we ready? Yes? So what exactly is the center of gravity? So center of gravity of an object is the single point through which the full weight of a body appears to act. So the center of gravity basically is where the force of the weight vector acts. I'll just show you that with a picture. If we have some mass like this, let's say it's m kilograms, this point where we draw the weight acting, this point here is called the center of gravity. And actually you can find that because it's the point where you can balance the object on a single point. So it's usually in the center, of course, the center of gravity. The way you can find it, I don't know if you remember the experiment to find it from high school.
Oh, yeah.
Do you remember it?
Yes. You hang it.
Yeah, you hang it and you draw a straight line down, and then you hang it from another part and you draw a straight line down, and where they meet is the center of gravity. Okay, but I mean that we can talk about some other time here. So the formal definition is the single point through which the full weight appears to act.
You don't need to know that.
What does your heart tell you? At least pretend to write it down. I have to collect my check once a month, and I would like to feel like my students were at least, learning something. So I hear your class rep. So this it's one of those things like after Donald Trump became president, people are saying, how did he become president? I mean, how? And now it's happened all over again in 2017. I thought we learned from that mistake. Oh well. So, what's your platform? Are you building walls or
Breaking walls.
breaking walls? I like it. Okay, breaking walls. Yeah.
Shorter lessons,
Shorter,
breaks.
longer breaks. Yes. Free money as well. People like free money too. You got that? Yeah. Nearly. Okay, continue. Yeah. So, how the mass is spread out will affect where the center of gravity is. So, for example, the center of gravity right now is in the middle, roughly, if I can manage it. Well, I'm tired. But you can imagine that if I was to put more mass on one side, the center of gravity would move. It will be changed. In other words, how the mass is spread out will affect where the center of gravity is. Okay? So if you have a lot here and a little here, then the center of gravity moves to the right then. Yeah. Okay, can I continue? Yeah. A lot of this stuff is just kind of, you naturally know it. You know, you're just trying to put the words to it. I think I might have a picture now. Another way to think of center of gravity is that it's like the average point. So it's kind of like an average, you know. Do you remember midpoint from maths? Yeah. Kind of like this for physics. Okay. Right, so we have three people here, and we want to think about who is the most likely person to fall. So in the three situations there, the father with his son, the mailman with the bag, and the woman with the books, who is most likely to fall, do you think?
The lady.
Yeah, well, I'm glad at least nobody's saying B. Okay, so that's good.
No, it's A.
Wait. We'll see. So you're saying C, and the reason?
The boots.
Yes.
The boots.
The boots. Yes, good. What about the boots?
It's mine.
Good. And your reason for A?
No, I changed to C.
No. Yeah, what was your reason for A?
Because a child is definitely more is heavier than both.
No, I think.
And also, she has one leg resting.
Yeah.
Behind.
Okay. Good.
So half of her weight, maybe not half, but some of her weight is more towards the left.
Good. These are all good reasons. Anything else?
The surface areas of like the way they're standing, the woman takes up more.
Yeah, this is all very, very good. So Fran had a good reason, you had a good reason, you had a good reason. And I'm glad that you all were thinking about these reasons. But there was one other thing that nobody has mentioned yet.
The height of the...
Yes, Nita, yeah?
I think his height is in one center.
Yeah, the height of the centre as
The
well
other one is her height.
is lower.
Yeah.
Yeah, that's the other thing. That's what I was looking for as well. That his centre is higher than hers, which if you think about it, makes something more likely to fall. Okay, but then Fuang said, well, her boots, it's smaller area. But then you said, or maybe it was you, that she has one leg back and one leg forward, so it's over a bigger distance, whereas he has both feet together. So you all have the right ideas. The reason for this picture is just to be thinking about what affects your ability to fall. Now, the person in the middle is not likely to fall, but he's not exactly balanced. Can you see his center of gravity is to the left?
Yeah.
Pull to the left then. Okay.
So what was the answer?
Oh no, this is one of those questions where its only purpose is to get you thinking. Yeah. But if you're asking for my opinion, I would have gone with A. The centre of gravity is higher and his feet are together. But that's just my opinion. I'm just glad that nobody said B. That's
You
all.
can get rid of the baby and he'll be definitely the most bigger one.
Yeah, but I think it's a bit safer to get rid of the books, because you can drop the books, but you're not really supposed to drop babies, I hear. Yeah. All right. So, in this lesson we have some more definitions. Fulcrum is another word for, I wonder if anybody knows, which is another word for, give me something simpler.
Point of rotation.
Yeah, which, I'm trying to break it down to the simplest synonym for fulcrum. Pivot is right, rotation is right, but turning point is the simplest one, yeah. It's another word for turning point, or pivot, or rotation point, or whatever. Pivot's another word for it. And it's the point at which an object turns, naturally enough. So if you can write this definition down. Yeah. These are words you know. You've heard these before? Yeah.
Well, I wrote them down as well.
Oh, yeah. But they're not exactly day-to-day words. Fulcrum, pivot. Yes, did you write this down, Omar? Yeah.
Lee, did you?
Of course.
Yeah, actually, that's a good question. Did you, Lee? Yes? Show me. Good. You're getting better. Good job. All right. So, the example I use every year, and I still have it here when I drew it with my marker, this here is a fulcrum, because this is the point where the door turns. So this is a fulcrum here. Okay. On the windows, Faisal, maybe you could point where the fulcrum is. Where do you think it is for the window? Yeah, there's two of them. Yeah, just like the door, there's two here. There's one down there as well. Okay, now you think about it. When I walk as well, here on the ground, that's a fulcrum as well, because my foot is turning on this point. Yeah, that's a fulcrum. Or here, when I pull the chair back, there and there is a fulcrum. So, in class, I could say fulcrum, I could say turning point, or I could say pivot. These are all synonyms. They're all the same word. I usually say turning point because it just feels the most natural. But I might sometimes say fulcrum or pivot. So you should write these names down. Okay. Continue? Yes? Yep. Right, for example, the hinge. That's called a hinge on the door. The center of a seesaw. Do you know a seesaw? Yeah. Yes? What's a seesaw? Tell her a seesaw. Explain. Go on.
Like when
It's a stick. One person sits on the end, the other person sits on the
Stick.
They go up and down.
The thing,
Go up
the
and
thing,
down.
the thing.
it's like
Oh, the key?
Yes.
Yeah.
Yes.
for the kids.
Where do you see a seesaw?
Playground.
Park. Yes. Yes. The wheels on the road from a car. What? They can vote you out of office, you know. The wheels between the car and the road is a turning point as well. Your foot on the ground when you're walking. These are all examples of turning points. Yep. Okay, so I think now we have some examples to try and help us what we were talking about earlier. So this situation is called very unstable. So what are the reasons this person is very unstable, the ballerina? Or not the ballerina, the gymnast.
Area.
Very good. Firstly, the area. Her hands are quite small. That's one reason. What's the other reason?
Center of mass.
What about the center of mass?
It's
It's high. But more importantly,
It's not in the middle.
Well, it is roughly in the middle, but more importantly, her centre of gravity is above the turning point. So it's like, yeah, you get it? So like, here you could hang this here, under the turning point, or you could have it here, above the turning point. And you can see, when it's above the turning point, it's unstable. But if I stuck it here, you know, under the table, then it's more stable. So even if I had some blue tack, any blue tack? No, okay. Imagine I had some blue tack. Even if I stuck it on the table with a little blue tack, it still would want to fall down. Okay?
Is that because of gravity?
It's because the centre of gravity is above the turning point. Yeah. It makes it unstable. So what you need to write down is very unstable. Two things. First, the area is small at the fulcrum, and the turning point, the centre of gravity is above the turning point.
Well, where's the turning point?
Yeah, good question. I'll pick on Fuang.
Huh?
Fuang, where's the turning point in this picture?
Above
Oh.
the...
Where?
Above the area.
Yeah, where is the turning point?
Where is the turning point?
Yeah, where is the turning point?
Hand.
The hands, yeah. The hands are the turning point here. Or more precisely, the hands in contact with the bar.
But then, when she does that, like her shoulders can be a turning point at first, and then.
Oh yeah, of course, so there's many things turning here. So I'm just talking about herself with her hands. But you're right, when her legs turn or when her shoulders turn, there are other turning points. Except these turning points, the difference is the turning point with her hand could disappear, whereas the turning point in her neck would only disappear if her head fell off. You know? So I'm more interested in the turning points that could be a problem. Yeah, but still it's good. Yeah, you're right. It is good to see that there's actually more than one in the picture. Okay, did you write?
Smaller surface area.
Small surface area at the turning point, and centre of gravity is above the turning point. Yeah. Lee, did you write that down?
Smaller surface area at turning point.
Yeah. That's the reason you gave me as well. You told me this.
Then I don't know how to write.
But you said it.
Mhm.
Okay, right. Alright, continue. The next one.
So if the turning point was below the.
Yeah, we'll get to that situation. We'll look at all the possibilities now. So next one. Notice how the centre of gravity is above the turning point and the base, her hands, are small. Okay? Next. So she could easily fall. So the coffee cup. It's unstable, but it's not very unstable. Because, true, the centre of gravity is above the turning point. The base, the area, is big. It could fall, but not as easily. But it could still fall. But not as easily as like this one. So this is unstable. Not very unstable, just unstable. Notice how the centre of gravity is above the turning point, but the base is pretty big. So it could fall, but you need some force. You need to, you know, it won't easily fall. You'll need to do something. Yeah. Okay. Yeah.
That means there are nothing.
Hmm?
There are nothing unstable 100%.
It's not 100%.
Nothing.
It's we still say it's unstable because it could fall. Because we could.
Yeah.
It could
I
spill.
mean, like nothing unstable 100%. Nothing.
I don't know. The previous picture is, I would say, nearly 100% unstable. Like
No, he meant like nothing is 100% stable.
Yeah.
stable.
Yeah.
No, but there's some things very, very stable. You know,
But not 100%.
Yeah.
nothing's 100% in life. Yeah. Okay. So this one, if you can write it down, unstable, The centre of gravity is above the turning point, if you can write that down. And the base here is pretty big, or at least bigger. Got that? Okay, next one is, I don't know if you've seen this toy. I had one when I was a kid. Anybody ever have this toy bird as a kid? No?
Oh, yeah.
You had it?
Kinda.
This bird, can you see here? The centre of gravity is at the turning point, and the turning point was the beak. So you could hold the bird, and you could put the bird's beak on your finger, and the bird would not move. It would stay balanced. Did you have this toy? Oh, you had it, great. And you had this toy? Or something like it?
I stole this one.
You stole the toy, great. Yeah. Anyone had this? No? So here the turning point and the centre of gravity are at the same location. And this makes it neutral. It's not really stable or unstable, because what you could do is you could take the bird and then you could move it, or you could shake it, and it moves but it doesn't fall, so it's not really stable because it's moving, but it's not unstable because it's not falling, so it's kind of in the middle.
So how does it balance with?
It's how the wings, yeah. The bird is carefully designed so that the mass in the wings and the mass in the body force the centre of gravity at the beak.
So you just touch the beak?
You can put it on your beak and you can put the bird's beak on your finger and it will just stay there. Yeah.
No.
See, I had this when I was a kid, and I don't know, I haven't seen them for years, so I'm sure you can buy one on eBay or something.
What's it called?
But I remember kids bringing them to school and they'd take the bird and they'd put it on their nose and look what I can do.
What is it called?
I don't know, it's like balancing bird toy or something on eBay. I don't know. Yeah, I don't know, you can see if it's on eBay. So notice how the centre of gravity is at the turning point, the beak. So even if there's a little force, it may wiggle or move, but it shouldn't fall off. But I suppose if you hit it hard enough, it will fall off. Okay, so this is neutral. Neutral is when the centre of gravity is at the turning point. Is it on eBay?
On YouTube.
It's on YouTube? Nice. But can you buy it on eBay?
Not sure, I don't have eBay.
You can probably buy. You can buy. They have on how much?
You can buy. Are you interested?
Kinda now. How much?
$6.
Sorry, when Lee said expensive, I was picturing $60.
It's for €1.
€1.
Amazon.
Get it.
I might order one tonight actually.
Well, it's an additional €0.70 for delivery.
Oh well, then forget it. Yes. Okay. Neutral. So neutral. The turning point is at the centre of gravity. If you can write that down, please. You got this? Yeah.
You don't have something like this.
Oh, it's like a dragonfly or something. Ah, yes, it's the same idea.
Yeah.
Nice.
And
You have this at home?
This is actually cool though.
it's in the direct.
Think of the possibilities.
This is great.
Yeah. 20 cents.
20 cents.
Yeah.
Oh, it's
There's oops. She has a Vietnamese version where the dragonflies.
oh, that's cool.
But the dragonfly's wings on arch.
They are in an arch pose in the picture
We
here.
just stay there? Doesn't make sense.
Yeah, it just stays there. Get it. Buy one. Okay. Right, so next one. So we've done very unstable, unstable, neutral, so of course the next one would be
Very stable.
very stable or stable. We'll go with stable next. So here, notice how the centre of gravity
What's neutral again?
is when the centre of gravity is at the turning point. And here in stable, the centre of gravity is below the turning point. So he won't fall, but I mean, of course he will fall if he lets go, but he's not very stable because his hands are quite small. So like his hands could fall, he could let go. Centre of gravity is below the turning point. So he's stable. If you shake him, he'll just move a little bit. But then after a few seconds he goes back to where he was. So centre of gravity is below the turning point and the base is quite small.
Question.
Yes.
This is more stable than the same man standing up on his feet?
Yes. Because people think, I was talking to the students in September about this before. You might think to say, I'm stable. But I'm not stable. Right now I'm unstable. Why am I unstable? My centre of gravity is above the turning point, and also my area is quite small. So you might say, if people are unstable, why don't they fall down all the time? What's the reason?
Muscles.
Yeah, but something
An
else.
applying force will remain.
Yeah, but something else.
The ground itself is
No,
okay.
no.
Like the center of gravity is aligned to
No.
the base.
Is it to do with our ears and the liquid to keep us balanced?
We're getting closer. We are unstable, but we don't fall down because of our brains. Our brains are able to stabilize, adjust. And if you think about it, that makes sense. Because I'm sure you've seen the videos of the robots trying to walk and they keep falling down. Have you seen those videos? So the robot, he tries to walk and then it's like, what? Because our brains are very good at keeping us balanced. But we don't even think about it, even though it's a lot to keep us balanced. Because we are unstable, not stable, unstable. Yeah. So if you think about it, this is why babies crawl on the ground. It's too difficult for them to walk because their brains haven't learned how to stay balanced. So when they're on the ground, their area is bigger because they have 4 instead of 2, and their centre of gravity is nearer to the turning point. Yeah. So this guy here is stable. Turning point is below the centre of gravity. Centre of gravity is below the turning point. So it should not easily fall. Okay, write that down, and then there's one left of these to do.
Does him falling down count as falling?
Yeah, these examples aren't great because of course he could let go and fall down.
Yeah, but then like falling as in like... Is that what they
It's
mean?
kind of, yeah, you see, the real word is topple, which topple is different to fall. It's hard to explain because there's not really a synonym for topple. So like if he lets go, he falls, but you wouldn't say he topples.
Yeah.
It's really hard to try and give a definition of topple.
So it's impossible for him to fall.
No, he can fall because he can let go, but he can't topple.
Yeah, topple.
Yeah. Now, you might have to look this up in the dictionary. Topple is not an easy one to explain.
I know what like topple means. Isn't it like...
It's a type of falling.
Yeah.
Yeah. Okay.
His hands are the only things that can fall, isn't it? Like that's what
yeah.
I mean by
Yeah.
topple. Like whatever is above the center.
Okay, think of it as handguards and weights.
Yeah, I was trying to put in pictures of people, which maybe is making it unnecessarily complicated. I just really, when I say not topple, if you push him, he'll just go back to where he was. So a topple is kind of this type of falling where it... See, the synonym for topple is not... There's not really a synonym for topple. A demonstration, yeah. All I can say is use a dictionary for topple. It's a type of fallen.
Just yoga.
Yeah. See the
Says
No,
overbalance.
but no. What I'm
yeah. Also, there's an expression in English, head over heels, which means topple as well. But anyways, it doesn't
what
matter.
I meant is like he can't fall. He can't topple.
You can't topple. No, you
Yeah,
can't. You
it's
can't.
impossible for him.
It's impossible for him to topple.
So
Yes.
why do they say so it shouldn't be easy to topple?
Because I put fall in brackets.
Oh.
He could topple.
Depending on the height.
Yeah, if you hit him hard enough, he will start. He'll let go and he'll start toppling.
Oh, but then that's because he let go. If
Yeah.
If he had something that was holding him.
Yeah, super glue. Yeah.
Yeah, then he wouldn't.
yeah. But this is thinking about it too much. Yeah. It's good to think. This last one is very stable because the center of gravity is below the turning point, and what else? Yeah, the base is quite big. So all of this would have to break before this falls. And even when you push this really hard, it just swings and comes back to the position it was in at the beginning. So this is the most stable because the center of gravity is below the turning point. It should never fall, really. The door will always swing back into a stable position.
What is that?
Oh yeah, what is this?
It's a dog thing, isn't it?
It's a dog.
Cat, yeah.
Dog door, yeah. Yeah. For your dog. You don't have these in Vietnam? No? That might be true, but that has nothing to do with this. Did you hear him?
Cats and dogs. Not only dogs.
No,
That they use.
Thank you for
That they
clarifying.
use
Yes. For cats and dogs. True.
Not that they cats and dogs, but the answer.
He's saying in Vietnam they eat cats and dogs.
Ah, yeah.
Yes.
Yeah.
Yes.
Is
So
it
he's
actually
saying.
true?
Yes.
Yes. Now you see, they
And
don't, but they don't eat like
They-
family dogs.
They say
They
that
eat the
very
dogs
delicious.
from like a dog farm, like how we would eat cows from a farm. No, you know, you saying that? No,
The dog.
they catch the dog. Oh my goodness.
Do you feel tempted when you're walking around in Ireland? Oh, this dog
Did
looks
you
tasty.
try it?
Huh?
Did you try it?
Try what?
The
Dog
dog.
eating it.
They want to know what it tastes like.
Like chicken.
I eat dog meat.
Is it good?
Yeah.
Depends
It
on the
is.
breed.
Yeah, different than chicken.
Different than chicken. Yeah, okay. Nicer than chicken?
Huh?
Nicer than chicken?
Yeah.
Really? Next time we're in Vietnam, we'll try some.
Oh no,
Yeah.
you try it.
Okay. I have a feeling eating dog meat is probably not halal.
Yeah.
Oh yeah.
It's haram.
It is.
Yeah. It's haram, is it?
Haram.
Haram, yes. Cats as well, right?
Yeah.
Yes.
It's only herbivores. You
What?
generally eat herbivores.
Oh, I see. And dogs and cats are not
Yes,
this.
the lion.
Anything that.
It doesn't matter. They can't eat dogs and cats. It's against their religion. So you'll just have to try for it. Yeah.
And describe it.
Yeah. Oh, so is this the reason for pigs as well then? Because they
Oh,
can
no.
eat meat, or it's a different thing?
No, it's a different thing.
It's a different thing. Okay.
Don't
Right.
eat meat.
Huh?
Pigs don't eat meat.
Pigs will eat pretty much anything.
Anything.
Anything. Yeah.
Yeah.
If a mouse falls into a pig's food trough, the pig will eat the mouse. It will eat anything. Anything that you put in front of a pig, it will eat.
Like the pig.
Yes. I know I won't tell you. Oh, I know I will tell you. So the business teacher went to okay. So I know you're not going to eat pork, but if you ever do, don't eat it in India because the business teacher said he was on holidays in India, and he was going to the bathroom, and it's flush the toilet, and the product goes down.
Yeah, I've heard about
You've heard about this, into a little box, and then all of a sudden you hear oink 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 oink, oink, and the pig's like, oh, some food. It's a type of recycling.
Oh, yeah.
Yes. So when I heard this story, I'm like, yeah. So, yeah. And that's not the first time I heard that story, because my physics teacher went to India and he told the same story as well. Now, I'm sure it's only in certain parts. I'm not trying to say the whole country is like this, but still, at the same time, if I was ever there and I saw on the menu,
I'll stay on the safe side.
yeah, I'd say I'll have the chicken, thank you. Yeah. Okay, so next definition now. Moment of a force. Does anyone know this one from high school? Moment of a force? Yeah. Do we have the formula for it?
Yeah, M times.
Yes. Distance from the pivot times the force. So the moment of a force is the force times the perpendicular distance from the fulcrum to the line of action. It is basically a turning force. Another word for moment is torque.
Yeah.
And as a formula, it's this. F times D. Now I'll explain with the door exactly what that means. The units, of course, if this is newtons and this is meters, then the unit here is Newton meters. So the units of Newton meters. I don't know, sometimes J or tau or gamma or L is used. I don't think I've decided. Yeah, I haven't decided which one I like to use, so maybe I'll just use L. Although I kind of like this one the most because it looks nice. Tau, yes. Okay. Have you got that definition? Can you write it down, please? Yes? Yeah.
So these are the units?
Newton meter is the unit. It's just there's different letters. You can use a J or a gamma or a tau.
Newton meter is fine though.
Newton meter is the unit.
Oh.
These are different letters for L, depending on the
Okay.
book you use. Okay, continue. You have this? Yep, alright. So let me explain with a diagram. So let's imagine here is the turning point. This could be like the door or whatever. And let's say this is the force. So I think I will use tau. No, I'll use L. The turning force is this force multiplied by this distance. That's all it is. So for example, if I open the door, the turning force is this force, my force here, multiply this distance, because this is the distance from here to the turning point.
So from where the force is applied.
From where it's applied. Now, it gets a bit complicated if it's at an angle, so watch this carefully. You have, there's two ways to do it, okay, so please watch carefully. Imagine the force was at an angle. You can say the turning force is this force, F, multiply not this distance, this distance from here to here, because this makes it perpendicular distance. So not this distance, this one. But there is another way to do it if you don't like that, and this isn't really what most people do in the exam. If you had this, what most people do, because it's what we usually do in physics, is we resolve, into a force this way and a force this way. And we'll call this one Fx, and we'll call this one Fy. Oh, sorry, and this one here is F. So the turning force, and this is D, will be D multiplied by Fy. This is gone because any force that goes through the turning point can't make it turn. So here, this force can make it turn, but if I try to put a force straight to the turning point, it's not going to turn the door. It has to be at some angle. You understand? Yeah. So, I think what most people do in the exam, because it's easier to do, is they think about it this way. They make an Fx and an Fy, forget about that, and just do this multiplied by the distance. And I think for most questions that's the easiest thing to do. Sometimes this would be easier, especially if they don't give you this angle, but mostly it's this one here. So maybe you want to draw this diagram, maybe you want to make some notes. You have two ways to deal with if it's at an angle.
So they won't give us the angle?
No, they usually do. I'm just saying, just in case. You have two ways to do it.
Question. Should we stay till 4 or till 4:34?
I think it also depends on the day as well. If she was in immigration at like 5 in the morning, then she's probably going to be gone at 4.
Okay, can I go and see her?
Is it important?
Yes.
Really?
Yes.
Honest?
Yes.
Okay, go.
Thank you. Yeah, I remember that I really wanted to go and see her, but I can't. Oh yeah, I remember.
Okay.
It's about my immigration appointment.
Don't be too long. We'll miss you. Okay, you got this? Yeah? Right, continue. So, it measures how much of a turning effect there is. In other words, if this turning force is big, then what is that telling you? Yeah, go on. What does it mean though? If it's a big turning force, what's happening? Is that what? Yeah. So, like, give me an example of something with a great turning force.
I have a question
Yeah.
about the previous.
Go on, yeah.
So when we connect them, we multiply the force by the distance of the.
Well, you see, it depends.
You wrote LF.
Yeah.
So
this force multiplied this distance.
Oh, so we still multiply.
Yeah. Oh, sorry, I never finished writing it in. I got distracted by something. There you go. What has a big turning effect? I suppose what's big? I'll give you a good example. If you have a car and it's stuck in some mud, you know mud?
Yeah.
You remember this? Mud? Yes? Car is stuck in some mud, and then what you do is you take a long stick, you put it under the car, and then you start to jump down on the stick to try and free the car. So this would have a big turn-in force. You're trying to move the car. Yes? Yeah. Okay, so A big moment means there's a lot of force, or a lot of distance too. So the picture here is if you have a big enough distance, if the D is big enough, even if the force is small, if the D is big enough, you can make the turning force big. So you could turn really heavy things. Yeah. Even if the F is small, here, if you can make the D big enough, you can make the turning force big.
Yeah, I was thinking about the example of the car.
Yeah.
Like instead of like standing on it and pushing it, what if you do know that tool that you can put on
the jack?
Yeah. And like if you put that and like you just
there's a different principle there for why the jack works. That has actually kind of more to do with gears actually than a turning force.
So like it kind of carries the car. No, not the jack. Sorry, it's like a thing that takes out the wheels, takes out the.
Oh yeah. The other thing, when you take the screws out of the wheel of the car, that has a great turning force because you really, really have to push down hard on it to turn the screws out.
If a car is stuck, they sometimes put it and they just accelerate, and then like it will kind of dig in the ground and carry the car out of the.
I have no idea what this is. Maybe it's something fancy that we don't have here in Ireland. We just have sticks and jacks.
No, it's the thing that takes out the screw.
The same thing, but I guess you stick it into the wheel in a way, and then you just accelerate.
Maybe it's only a problem when you have sand, or a solution when you have sand. I don't know.
Yeah. Probably some.
No, because like in Ireland, if a car's stuck, it's stuck in mud. So we have different ways than maybe if it's stuck in sand, because with sand it'll just keep the wheel will turn and the sand will just kick up, whereas with mud the car just sinks more into the sand. Different solutions for different climates. Okay, here's an example which I think you can try. It is with the car. A man is trying to free a car trapped in some mud. He uses a 2.2 meter steel pole. He puts the steel pole under the car's wheel and then uses a large brick as a pivot. The brick is placed 20 centimeters from the pole. The man pushes down hard to the end of the steel with a kilo newton of force. What's the moment? So he has his car is stuck. He takes his pole, he puts it under the car, and then he starts to jump down to try and move the car. So you have all the information there, and you have only one formula you need to use. This one. See if you can get it before I do it.
I lost you at steel.
Yeah. He has a steel pole.
No.
Oh, yeah. That's a typo, isn't it?
Yeah.
S-T-E-E-L.
Again and again.
Again and again.
Yeah.
Oh.
Oh, rats. Rats. Why did I do that? Yeah, no, I did something similar in the exam as well. I said a boat sails. Instead of typing S-A-I-L, I typed S-A-L-E. Okay, try to do this one. Actually, we won't miss a chance to use the calculator. Okay, are we nearly finished?
Yeah, 2000.
What did you get?
2180.
I don't know. 2000 was sounding better to me. Did you do 2.2 multiplied by 1,000?
We're supposed to minus the
100.
Wait? No?
What?
1000. It's kilonewtons. No.
Can I do it?
Yeah.
Right, so look. Got what you needed? Now, explain to him why it's 2,000. He explained seesaw to you. Now you explain to him why it's 2,000. Go ahead.
The brick, the distance between the brick and the car is 0.2 meters.
Yeah, 0.2 meters.
Yeah, so the other side, the distance is the distance.
And what's the distance?
2.
2 meters, yeah.
I multiplied 2.2 by 1,000.
That's what I thought, yeah. And here, what's the force here?
1 kilometer.
Which is how big?
1,000.
That's it. 1,000 newtons. So the turning force is 2 times 1,000 because it's from here to the man, which is 2,000 Newton meters, or in other words, 2
Newton meters.
yeah, kilo. Okay. Right, one more. Try this one. A wrench is used to tighten a nut. The wrench is 20 centimeters long, and the force being used to tighten the nut is 100 newtons. What is the moment of this force? 20. Yeah. So what you have here is you have a wrench. This is a wrench. So this distance here to here is 0.2 meters, and the person's hand which side would the thumb be on? So who's the artist? Lee, okay, yeah. Look, you can tell it's a hand because I put an eye watch on the wrist. Yeah.
I
So
don't think the eye watch should be using the wrench.
no, this is what did I say? 100 newtons, wasn't it?
Yeah.
Yeah. So the turning force is 0.2 times 100, which is 20 Newton meters. But in the question I said it's not really this much. It's actually less than this. And why is the reason that it's less than this? What's not right about my picture?
The screw is too small.
No.
He's not holding it from the end.
2 reasons actually, yeah. The first reason is, well, the force isn't really at the end, is it? It's more like around about here. And also, the turning point isn't here. It's more like here. So the distance isn't really 20. Maybe it's only like, what would you say?
15.
Maybe 15. Yeah. Okay. So the turning point is actually here, not at the end. And the force isn't really at the end because nobody holds the wrench like this. You hold it like this. Yeah. Okay. Great. I think I'll let you try these for 5 minutes. And then we'll have a start of the next lesson then. The first 3 questions are just examples you need to give me, and number 4 is the only calculation question. So in fact, I think you could do all of this in 5 minutes, and then I'll do the answers. So see how quick you can do them. So the first one, give me something that's stable, and don't give me the one I gave you. Any 3 examples for 1, 2, 3?
The stable one is the ceiling fan.
No.
Yeah.
Okay. Ceiling fan then.
What is that?
No, see, I picked something strange. So.
Ceiling, not this room, but normally there's like a fan.
Cloth hanger.
Yeah, this is more, clothesline, something like this. Come on, write down some examples, and then more important is the calculation question number 4.
How are we going to find something that's neutral? Other than that, right? I've never seen anything do that.
No.
Neutral. I'll give you an example. If you could balance your calculator at the center, or let me show you neutral right now. This can only end well.
Can I film that?
Hang on. I can do this.
I can do it.
No, don't touch me. No, not quite neutral. But neutral just means the turning point and the center of gravity are at the same location. So a teacher balanced his chair backwards would be neutral. Well, no, that's not really neutral because the center of gravity is above the turning point. A better example would be like your calculator balanced on your finger.
But then the center.
No, because it's, look, it's neutral. Even though I hit it, well, that's too hard. It just wobbled a little bit. It didn't move. Do you know what I mean?
It's stable neutral.
But then isn't the center of gravity like in the middle?
Yeah, it's about in the middle. No, stable and neutral aren't really the same thing. Stable is better than neutral. Huh? Table?
Is it neutral?
Table will be stable because the center of gravity is here. The turning point is here. So it's above the turning point. So that would be stable, not neutral. Neutral would be like the calculator on your finger, for example. Yes. But if you could write something down, that would be great. And yet nobody clapped. Okay, what's an example of something stable?
Table, cloth hanger.
Sorry, I said table was stable.
Yeah.
I totally misspoke. I'm so
Yeah.
sorry. I meant to say unstable. Because the center of gravity is above the turning point.
It's like us.
It's like us, yes, yeah. So what's stable?
Cloth hanger.
Yeah, something hanging on a washing line. What's unstable? Table. Coffee cup.
An empty coffee cup, can it be neutral? But it doesn't have much mass, so it could be in the
An
box.
empty coffee cup with a heavy base. The center of gravity here is still quite high. In fact, funny enough, not an empty coffee cup. A coffee cup with small coffee in the bottom would be more stable because the center of gravity is pulled down.
So like a shot glass would be stable.
This with an espresso would be stable. Yeah. What about neutral? Well, if you balance something on your finger like a calculator, that would be neutral. Okay, try number 4 now, which is the calculation.
Equal masses on each end.
Yeah, seesaw with twins on each end. There are twins in the science group. We can test it out sometime.
Oh, they're not very identical.
Okay, well we can test it then. Right, try number 4 now.
I finished.
Did you write it down?
I finished.
Write it down. One Lee is enough in class. I don't need two. Good. Okay, I'll just give you 2 more minutes, then I want to do the answers now.
All of the examples that we'll do are uniform thingies.
There's 1 or 2 exam questions are not uniform.
And it's only one force.
Oh, for this lesson, but very soon we'll add more to it. Come on, Faisal, write the answers down, please.
Moment force and turning force are 2 different things.
No, they're the same thing. They're just,
Same formula.
yeah, it's just they're just synonyms, really. They mean the same thing. Turning force, torque, moment. They're all the same thing.
So if the force was applied from one side and then another one was applied from the other side, they cancel.
We'll do that soon. Yeah. Yes.
The moment of force like the book.
It's like it, but it's not it. It has the same units. I know it's the same formula, but it's a different thing in a different situation. So here, we haven't done this yet, but the difference here is the force, and then here is the distance. This is linear, straight line. Here is the distance, and here is the force, and this is perpendicular, and this is not linear. So I know, Lee, the formula is the same, but the situations are different, which means what it represents is something different. You know what I mean?
What's the problem? What's the problem?
What's the purpose of this?
Yeah.
The purpose of this, the purpose is, it's the force that makes it turn. So, if something is turning a lot, it means there's a big turning force. So this is important in engineering. We'll see later when we're talking about like gears, cars, machines, where parts are turning. So something turns here, something else turns here. We want to know how much force could turn. The car is the most important example because you know the car engine, it's turning and it makes the wheels turn. So we want to know how much here and how much here. Yeah. Okay, let's have a look at the answers now. Right. Can I do number 4 now? So the first part. Part A of number 4. Here's the swing. How long is it? 5 meters. It's a long swing. 3 meters. 3 meters. And the boy sits here. And the father is here. And the force is how much? 100 newtons. So the turning force is 300 newton meters. Part B. Yeah, the father swapped place with the boy, but because the force is the same and the distance is the same, the answer is the same. It's kind of a trick. In other words, my point here in part B was it's not important about the mass here. Okay, what's happening in C? The boy now jumps on a seesaw by himself and it's 5 meters long. What's the moment?
It's kind of forced then.
45 times 1.81
Yeah, times what?
2.5.
So here's the seesaw.
Calculator.
Yeah, this is 2.5. This is 2.5. This is the boy. And the boy is 40 kg. So the force here is 40 g. And the distance? 2.5. So the turning force is 2.5 times 40 times g. Well, what's the magic? (2.5) times 40 times 9.81, 981.
Where'd you get that 40 from?
The mass is 40. It's yeah, it's given in the question.
Not that.
This one?
No,
This one?
40 grams.
Ah, no, that's 40 g, 9.8. Yeah, it's his weight. mg. Yeah. Okay, what's part D now?
So is the boy still on the seesaw?
Yeah, if the father jumps on the other end of the seesaw, then how much moment does he apply? Okay, so I want to know, oops, if the father is here, how much will he apply? So it's the same idea, except what's different with the father?
400.
It's mass. What's his mass?
100.
100. So it's going to be bigger for the father.
2,000.
2.5 times 100 times 9.81. 2453.
But then is the kid still on?
Yeah, I think that's the next one, and the kid is still on it. What is the total turning force? So if you think about it, here's the seesaw. Is this part E? Yeah. The boy tries to make it turn this way with 981 newton meters, and the father tries to make it turn this way with 2,453 newton meters. Who will win? The father. In total, it will be 2,453 minus 981. Yeah? 2,453 minus 981. 1,472 newton meters. Yeah. And now, lastly, the father and son now sit on the swing together. The father takes a few steps back, bends his legs, and swings. The angle is 30. What's the moment? Okay, so this one's a little bit tricky. Watch carefully. So what happens here is both father and son sit on the swing. There they are together. Don't they look happy? What's their combined mass? 140. Yeah. Now, what's happening here is there's a 140 G force here, but actually the problem is it's at an angle. What we need to do, we don't care about this part, we only care about this one, because this is the one that's perpendicular. Now, you have to be careful here. I tell you that this angle is 30. So this angle here, oh my goodness, let's draw a triangle. This one here, 90. This one here, 90. That one's 30, that one's 90. This one here, no, 60. This one here, 30. So this one here, 60, because this is 90 here. So finally I can say this is 140G. Cos or sine?
Cos 60.
Cos
Or sine
60.
30.
Or sine 30. Oh, yeah. Yeah. And what's this distance from here to here?
From where to where?
Here to here? We said 2 meters, I thought it was.
2.5.
No, the swing.
Is 3.
3. So what's the turning force here? It will be 149.81 cos 60 times 3. (140 times 9.81 times cos 60 times 3. 2060 Newton meters. So we don't care about this one. We care about this and this. But actually we don't care about this one because it's through the turning point. We only care about the one that's perpendicular. That one was a little bit hard. Yeah, question?
Too many angles.
Yeah, let me try and draw it again with less angles in it here. So this angle here, I tell you, is 30. Happy with that?
Yeah.
And this one is going straight down. That's the weight. And we want to know this part, and we want to know this part. Now maybe you know from maths class in high school that if this angle is 30, this one is 30 as well. Because there's a proof in maths that says, yeah, this angle here is the same as this angle here. So that's the situation you have here. This angle is the same as this one. So if that's 30, then this angle here is 60. So this is W cos 60, and this is W sine 60. Or you could have said, if that's 30, then this one here is the cos. You get the same answer. That's the same thing. I know this last one was hard. Yeah, okay. If you want, we can say this one is W cos 30, and this one here is W sine 30. Will I go back to the main picture? It's tricky, I know. Okay. Continue. Don't worry, this is going to be uploaded later today. We'll have